Hi everyone. This video is meant to help you understand sampling distributions and the central limit theorem, which are two ideas that we talked about in our last class. This is showing a simulation website called Rossman Chance, and I'll explain what this website is showing. Right here, in this window, you have a population of 18,000 people. Their ID numbers go from person 1 all the way up to person 18,000. This window is showing the hours slept per night by each person in the population. So person 1 is getting 6.5 hours of sleep per night, person 2 is getting 6 hours of sleep per night, and so on, all the way down to person 18,000, who's getting 7.25 hours per night. Down here, we can see the 18,000 people in a histogram. We can see that the population has a roughly normal distribution, because in this population, there aren't very many people down here who are getting 4 hours of sleep per night, and there aren't very many people up here getting 12 hours of sleep per night. In this population, most people are somewhere in the middle. It actually looks like most people are somewhere between 5 hours and 9 hours of sleep. Right here we can see that the population mean, or mu, is 8.001. That means that if you added these 18,000 sleep times and divided the total by 18,000, you would get 8.001. So like I said, the population mean, or mu, is 8.001. That's why the population is centered at 8. Remember that if a population has a normal distribution, the mean is at the center of the population. The population standard deviation, or sigma, is 1.51. That means that if you took these 18,000 sleep times and plugged them into the standard deviation formula, you would get 1.51 as your answer. The population standard deviation, or sigma, is measuring the amount of spread, or the amount of dispersion, between these 18,000 sleep times. Over here, we can see a random sample of 10 people from the population. These are their 10 ID numbers, and these are their 10 sleep times. Down here, we can see the 10 people in the sample inside of a graph of their own. These are their 10 sleep times. Right here, we can see that the sample mean is 9.4. That means that if you added their 10 sleep times and divided the total by 10, you would get 9.4 as your answer. We can also see that the sample standard deviation is 1.515. That means that if you calculated the standard deviation of these 10 numbers, you would get 1.515 as your answer. This sample standard deviation is measuring the amount of dispersion between the 10 people in the sample. It's measuring how spread out these 10 dots are. Over here, we can see the mean of this sample as a building block. So this block right here is just showing the mean of the 10 people in the sample. If you add these 10 numbers and divide the total by 10, you get this number right here. This is just showing the sample mean of 9.4. Now what if we wanted to create a graph that showed not only one sample of 10 people, but the means of lots of different combinations of 10 people from the population? We could actually create that type of graph. We would just say that we want a large number of samples of 10 people. Let's ask the website to give us 1,000 samples of 10 people from this population. After we click on Draw Samples, it'll show the means of 1,000 groups of 10 people from this population. Each building block inside of this histogram is just the mean of a different combination of 10 people from this population. So this blue line right here is the mean of these 10 people. This blue line is the mean of these 10 people. This blue line is the mean of these 10 people, and this blue line is the mean of these 10 people. So this is basically just a stack of building blocks, and each of those building blocks is the mean of a certain combination of 10 people from the population. In class, we said that a sampling distribution includes the means of all possible samples of a certain size. This graph actually isn't showing the complete sampling distribution for combinations of 10. That's because this graph doesn't show the means of all possible combinations of 10. It's only showing the means of 1,000 combinations of 10. There's actually many more combinations of 10 in this population than just 1,000. However, since this graph is showing the means of lots of different combinations of 10 people. The shape of this graph is pretty close to what the shape of the complete sampling distribution would be. In other words, the shape of this graph is a pretty good approximation of the shape that the complete sampling distribution would have for, for the means of all possible samples of 10. And we can see that this pile of sample means has a normal distribution just like the population. That's because when the population is normal, the sampling distribution is always normal, no matter what sample size you're dealing with. So before we move on, I want to remind you that each building block in this histogram is the mean of a different combination of 10 people. This is the mean of these 10 people. This is the mean of these 10 people. And this is the mean of these 10 people. So we're just looking at the means of different combinations of 10 people. And those sample means have a normal distribution because the population of individual people has a normal distribution. Now, what if we looked at a different sample size? For example, what if instead of looking at the means of combinations of 10 people, we looked at the means of combinations of 20 people? We could actually do that with this website. We would just have to say that we want 1,000 combinations of 20 people, and it'll create the graph for us. Now, in this graph, each building block is the mean of a certain combination of 20 people. This is the mean of these 20 people. This is the mean of these 20 people, and this is the mean of these 20 people. This is basically just a pile of building blocks, and each building block is the mean of a certain combination of 20 people. And just like when we were dealing with combinations of 10 people, these sample means have a roughly normal distribution, just like the population does. So when the population is normal, the sampling distribution is normal, no matter what sample size you're dealing with. Now, what if we looked at combinations of 30 people? In this graph, each building block is the mean of a certain combination of 30 people. This is the mean of these 30. This is the mean of these 30. And this is the mean of these 30. The sampling distribution still has a normal shape because the population is normal. So remember that the central limit theorem says that if the population is normal, the sampling distribution of sample means is always normal, no matter what sample size you're dealing with. The sampling distribution will be normal for combinations of 10, for combinations of 15, for combinations of 20, or for any sample size. Now, what if we switched to a different population? What if we switched to a skewed population, like this one right here? This is a skewed population because most people in this population are getting lower amounts of sleep. There's fewer people who are getting higher amounts of sleep. Let's do the same demonstration over again, but with the skewed population. So let's look at 1,000 combinations of 10 people. This histogram is showing the means of different combinations of 10 people. So this is the mean of these 10 people. This is the mean of these 10 people, and this is the mean of these 10 people. We can see that this sampling distribution is skewed just like the population. So when the population is skewed, the sampling distribution will be skewed just like the population when you're working with a small sample size, like combinations of 10. The sampling distribution isn't as skewed as the population, but it still has the same type of skewness. It still trails off like this. If we go up to a bigger sample size and look at the means of combinations of 20, the sampling distribution will be less skewed. It'll be more normal. Because the central limit theorem also says that if the population is skewed, the sampling distribution becomes more normal with bigger sample sizes. In this graph, each building block is the mean of 20 people. This is the mean of these 20 people. This is the mean of a different group of 20 people. And this is the mean of another group of 20 people. But all of these sample means have a roughly normal, sort of a roughly normal shape because we're dealing with a bigger sample size. Now if we go up to combinations of 30, that's really the point when the sampling distribution becomes roughly normal, even though the population is skewed. In this graph, each building block is the mean of a certain group of 30. So that's the mean of these 30 people. That's the mean of these 30 people. That's the mean of another group of 30. So there's lots of different combinations of 30 in this population. And each building block in here is just the mean of a certain combination of 30 in this population. But these sample means in the sampling distribution have a roughly normal shape, even though all of these groups of 30 people are coming from the skewed population. So basically, what the central limit theorem says is that if the population is normal, the sampling distribution is normal for any sample size. It doesn't matter if it's combinations of 5, combinations of 10, combinations of 15, or any sample size. If the population is skewed, the sampling distribution becomes more normal with bigger sample sizes. So the means of combinations of 10 won't be very normal. The means of combinations of 20 will be more normal. And the means of combinations of 30 will actually become roughly normal. And if we go up to a bigger sample size and look at the means of combinations of 40, the sample means and the sampling distribution will become even more normal, because the further the sample size goes up, the more normal the sampling distribution will become. So in this distribution, each building block is the mean of 40 people. So here's the mean of these 40, here's the mean of these 40, here's the mean of these 40. Basically, we're dealing with combinations of 40 people now. But when the population is skewed, the sampling distribution, the collection of sample means, becomes more normal when your sample size goes up. So since we're dealing with combinations of 40 people, and each block is the mean of 40 people, the distribution became even more normal. And if we went up to 50, like this, it should become even more normal. So now each building block is the mean of 50 people. That's the mean of 50. That's the mean of 50, and that's the mean of 50. It became even more normal because we went up to an even bigger sample size. So remember, the central limit theorem says that if the population is normal, the sampling distribution is always normal. If the population is skewed, the sampling distribution becomes more normal with bigger sample sizes. And before I close this video, I wanted to show one feature of this website that I think is pretty helpful. When you click on a low sample mean down here, you'll notice that the people in this sample are toward the lower end of the population. They have lower values, and that's why they have a low sample mean. And if you click on a high sample mean up here, you'll see that those people have higher values, which is why that sample has such a high sample mean. So I think that the reason why this sample mean is so high is because of these people, these sample members, up here who are bringing up the sample mean. So these 50 people have a mean of 8.6 up here. I think they have such a high sample mean because these people are bringing up the sample mean. I think that this feature becomes a little bit more clear if we go back to a smaller sample size, like let's say 5. So I'll have it give me, it can do it one at a time also, but I'll do 1,000. So right here, we have a low sample mean, and it makes sense that these 5 people are at the low end of the population. So these 5 people have a mean of 6.5, which is down here. And it makes sense, like I said, it makes sense that they have such a low average because they're at the low end of the population. If we go up here and click on a high sample mean of, like a sample mean of 10 right here, we'll notice that these people are at the high end of the population. Since these 5 people are at the high end of the population, they have a high sample mean. So overall, if you click on a low sample mean, you'll see that the sample is at the low end of the population. If you click on a high sample mean, you'll see that the sample is at the high end of the population. And if you click in the middle, you'll see that the 5 people are in the middle of the population, because when you have 5 people who are in the middle of the population, their sample mean ends up being somewhere in the middle.